Thank you for welcoming me here in Saint-Étienne. So I will present my PhD subject, which is about additive manufacturing by stereolithography of ceramics, which are here zirconia for biomedical applications. And I will try to focus a bit more on the study of the laser photopolymerization in this process. So I work at MatéIs lab in Lyon, and my supervisors are Guillaume Baeza, Jérôme Chevalier, and Hélène Révent. So first, about my PhD outline to make you understand which part I'm going to talk about. I have 3 states of the material in my process. So I focus my work on these 3 steps. At first, I have stereolithography pastes that are made of photopolymerizable resin plus ceramic particles. And I do mainly mechanical, so rheology experiments on it. I also work after the printing process on my polymerized objects. So this is what I'm going to focus on, about the polymerization characterization, and then also on the thermal phenomena that they endure during the debinding and the sintering. So for these first experiments, I work on my own homemade pastes and objects that I developed, and I also work with some references from the market, which are made by 3D Ceram. And also, after the debinding and the sintering step, I have sintered ceramics that are dense and prepared for their use. And I'm going to present a bit these results too, because it made a publication just a few months ago. So for the outline, first I'm going to explain the context about the biomedical part, and then the rheology. So each state of my subject will be treated, but with a focus on polymerization. So first, why do we do this project? It's because we wanted to improve specific implants that could be made in ceramic, so that are used for cranial or maxillofacial surgeries. So how can we improve them? By making tailored geometry to really adapt for the needs of each patient. So these are some parts made by 3D Ceram and something we managed to print also for the dental industry. And how did we choose this technique is because it's the most mature in the printing of ceramics in the industrial and clinical aspects, and it's the most accurate, so it's SLA stereolithography. Then we want also to improve osseointegration. So for that, we have 2 ideas. It's making structures at the micrometer scale and also at smaller scales to promote adhesion and vascularization of the implants. And also want to improve the mechanical reliability of our samples. So with that, we used some ceramics that have plastic behavior that are really well suited for 3D printing, because it can hinder crack growth if we have inner defects, which happens a lot in 3D printing. So for the presentation of the stereolithography process, here on the left, you can see that at first we add from the syringe some paste to form a new layer. So we add the paste and we scrape it in order to have a very thin but very regular thickness of our layer. And then we can make the polymerization following the pattern that we want to add the new layer. And we do this layer by layer. Then we remove the unpolymerized paste and make the debinding and the sintering step. So what is specific for this technique compared to other photopolymerization techniques is that we use paste deposition. We don't use a cube with resin on it. And we have very thin layer height, which permits us to have a very good accuracy. So you have this error of around 70 micrometers on a dental bridge, which are surfaces that are pretty difficult to make. And also we have a good surface state. So you can see a bit the laser, the pulse laser process for different shapes on a layer. And now talking about the paste, so you can see when we shear it, how it behaves, and a small schema that shows that we have here powder, so mainly powder, half of the volume. So small particles of zirconia for us to have small grains and good mechanical properties. We have monomers of acrylates that permit a fast polymerization, And this polymerization is permitted by photoinitiators. When they receive UV light by the laser, they will begin the polymerization. Then we have dispersants to make it flow well and achieve a good density, and also plasticizers to have a good thermal treatment when we debind, so when we remove the organics from the material. So at the end, we only have the powders that are linked together and that grow to make a full ceramic implant. So talking just a bit about rheology, why do we need to study rheology of our paste? It's because we need two main properties. We need it to be self-supporting. So we need to have a bigger elastic modulus than the loss modulus, G prime bigger than G double prime, because we need to have more solid than a liquid that flows. When the paste is scraped, we want to keep the layer constant, the layer thickness constant. So that's why we want to achieve this property. We want also to be well spreadable, so have a low viscosity at high shear rates permits this, and also to avoid shear thickening, because if we have shear thickening, it's an increase of the viscosity at the considered shear rate, which is very high. So the shear rate depends on the very small thickness of the layer and also on the speed of the scraper. So if we want to achieve a good spreading, we need to have a low viscosity at this shear rate. So it means we want high viscosity at rest, low at high shear rates. So we need a shear thinning behavior, which corresponds to this type of behavior. So now talking about photopolymerization, first I wanted to use a model that has been developed to calculate the received energy in the volume of the paste. It's not something that is always done when we try to characterize the photopolymerization. And here I wanted to understand how much energy has been received by each voxel in my sample. So I used this model which calculates the energy received by one pulse, and you see the dependence on several parameters that I can change during my process. So it permits me to adjust the process making these calculations. And you see that you have a diffusion pattern when you throw a pulse. So at 100 micrometers in X and Y, you have an effect. You receive also energy from this pulse. And you can see when you take a cross section of it that you have a tenth of the energy received at even 150 micrometers. So it means 6 layers. So it's pretty impressive, and it permits us to continue to polymerize the lower layers, to have a good bonding between the two layers, and to have a good surface state and better properties than what we can achieve with other techniques of 3D printing. So based on this model, after I add all my pulses following the thing on top. So here there are also a few parameters I can also change to make the distances vary between the different pulses, and to change the, it's not me, no, and to make also the different lines spacing to make my part homogeneous. So here you can see it going from one pulse to one line to one layer. So you see the layer is very homogeneous in terms of energy, so it's nice. And here EC is the critical energy, and what I have seen with these parameters that I have chosen for the demonstration is that we reach this energy even at 190 micrometers, so much lower than several layers. So here, after that, you see this kind of pattern when you add all the layers on top of themselves. And what can be a bit surprising at first is that you have lower energy received on top than on the lower sides, because we added the energy each time. And this is very important for the characterization of polymerization. If we do analysis on the top of the sample or in the middle of the sample, we won't have the same conversion rate, and we need to achieve the highest conversion rates of our polymers to avoid having a bad debinding where we could have some thermal polymerization or some cracks due to this difference of conversion between our polymers. So here's just an example of, on the left, some parameters that have been chosen that show non-homogeneity and could make bad samples because of that. So here I'm gonna just show you some results of, so first, how do we make chemical polymerization characterization? So using a FTIR method. So this is some part of a spectrum that has been made for a paste, so zero polymerization, and for a printed part that has been polymerized. And here you can see on my monomer the different species that you can locate on the spectrum. So what is very important is the first peak that corresponds to C double bond O, which doesn't move when we have polymerization because it's always in the monomer or in the polymer. So this peak won't change, and it will be our reference to see the variation of the heights of the other peaks. And these peaks, these other peaks, will change in height because they disappear during polymerization. So this way, we will be able to characterize the percentage of conversion of our polymers thanks to that. So here also I show you just a small focus on how do I calculate my area, because some other peaks can perturbate my calculation, so I have to locate them well. And then I also use NMR spectroscopy, but we haven't done all the treatments on this data, so we have good results for the beginning, but I will explain you, I think the next time we will have a better progress on that. So showing you more results about that here. The results for FTIR spectroscopy, it gives us the evolution of the conversion rate depending on the mean energy on the zone that I studied. And what you see in pink is that it increases on the top of the sample when we made the measurement on the top of the sample. And you can locate the energy at which it doesn't increase anymore. So it permits us to locate what are the parameters of polymerization that are sufficient to provide the polymerization we need. But the problem is that we have some inhomogeneity. We have a point which is much higher than what we are supposed to have. And this is because we characterize the top layer. When we characterize the milled samples or the overall sample, you see that the values are upper, and it's because I showed you the figure with the energy discrepancy when you go on top, because you provide less energy. So this technique permits us to have more reliable results and to locate well how much energy do we need to provide for having good polymerization. So we can locate the plateau. And also here, so the first results for NMR gave us the same trend about the energy. So it would be a very nice thing to have another way to characterize polymerization, but with physical rigidity instead of group conversion, to provide more understanding on the way it polymerizes. So now focusing more on the mechanical part, I'm going to show you results on ceria-based zirconia composites. So it's different zirconia. And why do we use this type of zirconia? Before this work, during 40 years, there has been development of this doping of the zirconia to permit it to transform. So when you have a sufficient mechanical stress, you have a local transformation to permit a bigger change of the geometry of the sample, and to have a type of plasticity that we can't achieve with the other ceramics. So here what you see is the surface of a ceramic that is subjected to 4-point bending tests. And what you see, it's not cracks, it's transformation bends where we have transformation. So here on the mechanical characterization curve, you see that we are at the first point, that when we increase the load, we have more transformation, and more transformation. And so we made studies to understand why the transformation was located on some peaks and not other peaks. So what you can see here, that it's volumic transformation, it's not only lines. You see that there is really a volume pattern on the transform layer. But this wasn't expected because it didn't transform this way before. So what you can see here is that on the left part, we used to have bigger bends that didn't grow on top of themselves. They would grow, but you wouldn't have very thin bends adding and adding the way we had it. And here is one reason why we have that. So this is our microstructure, and what you see on the left is that you have several different phases. So the long phases that are black are strontium aluminates, and the fact that here they are very well homogeneously distributed and here not distributed at all, it makes here the growth of the bands of transformation change. The bands will grow with more facility on the patterns of heterogeneous structures of strontium aluminates. And so because of that behavior, we could have a different mechanical behavior, so more strain is achievable. But here what we saw is that we weren't able to achieve exactly the same distribution of strength because it was the first development of this material. So we want to improve the distribution to make the material more reliable. So what is the parameter to look here? It's the M, so it's the Weibull modulus, which shows us that with our traditional way of processing these materials, we had better distribution, so a thinner distribution. You see that the lower strength were higher than the lower strength we have for the pink ones. So this is where we can improve on this stereolithography for these samples. So now, for the conclusion, let's talk about real parts. So we have some bone scans of mandibular parts, but it's not exactly the design that we want for bone replacement. And because my material is very expensive, also we don't want to make this type of mandibula just without any sense. So we need to optimize the geometry of the parts that we want to print. And we are currently working with clinicians to have a benchmark of clinical cases where some parts could be designed and where it could be really something interesting to use this material for printing because it's more resistant. So then after that, we will be able to make the texturation patterns on an interesting surface of our sample. But first we need to choose exactly the parts we want to make. So to make just a small insight on what I said, we have found the rheology requirements that we need. So we were able to make our own paste thanks to that. We are able to characterize the physical and chemical polymerization so we can choose the right parameters. And we are able to print ductile and defect resistant ceramics with interesting mechanical properties so that they can hinder crack growth and be more reliable for the clinical industry. So thank you for listening to me, and you can ask me questions.